Silence.
I feel like we should start. Maybe we should. Okay, do you mind if we start? Okay, welcome. Thank you all very much for coming this evening. My name's Dan Cottle. I'm Associate Professor of Physics Education here at the University of Birmingham. This is the second in our series of public physics lectures this academic year. You've only missed one if this is your first time. But we've got a really great speaker and a great topic tonight. It's just flicking through on the screen up there. It will come back on in a minute. Before we do start, I should just remind you that if you haven't found the toilets, let me just remember where the toilets are. Basically, they're either on this floor or go downstairs and on the next floor. If you need them, feel free to use them if you want to. We have a whole programme of further lectures this academic year, including one on the first Tuesday of December. So we'd like to welcome you back for that if you're interested as well. But without further ado, I'm going to introduce our speaker for this evening, who is from this very department and is Dr Ben Gompertz. So shall we welcome Ben with a round of applause?
Thank you everyone for coming out. It's great to see so many of you here. Hopefully I've got all the various microphones they put on me turned on so you can hear me online and in the room. And I'm talking today about what is the subject of my research here at Birmingham, which is neutron star mergers and the effects that they have on the universe we live in terms of the chemical enrichment and the building of some of the most massive elements in nature. So if you look up at the night sky, which I hope all of you do sometimes, it's easy to think of it as a static and non-changing thing. With the naked eye, we can see maybe a few thousand stars that don't change from night to night. But actually, if you can see to faint enough limits, the universe is alive with explosive transient events that go off probably twice a second is the rate for supernovae. And so the image here is a real photograph, not a real animation, of the VLT, the Very Large Telescope in the Atacama Desert. And you can see the beautiful dust lanes of the Milky Way arcing across from the horizon. And those points of light that keep popping up are, of course, not real. Those are animations of the rate of supernovae that we see coming from very distant galaxies all across the cosmos. As I said, at a rate of about 2 per second. So the universe is alive with these events, and they have really a very profound impact on the universe we live in. And they alter the composition and build some of the most massive elements that we see. And so it's an important question to ask, of course, as we look around us and all the complexity that we have on Earth and all the different chemicals and elements that we use in industry, in our day-to-day lives, in jewellery, etc. Where did all of those come from? So I'm going to start with a bit of a history of the universe. In the beginning, which is one of the grandest sentences you can say, we had the Big Bang. And the universe was a hot, dense plasma of quarks and gluons for the first fraction of a second. And within the first second, the first elements formed. Those are the protons. The number of protons defines the type of element you have. And if you have one proton, that's hydrogen. So hydrogen was born in the first few seconds of the universe. And within a few minutes, the universe had cooled enough that hydrogen could be fused into deuterium, which is one of its isotopes, and helium, and trace amounts of lithium. So all the hydrogen and helium that you have around us is ancient. It comes from the very first few seconds and minutes of our universe. And the universe back then was very different to how it is now. It was completely opaque. Photons could not travel until the universe had cooled enough for electrons to bind with atoms. And that took something like 380,000 years before you could see through the universe and observe it the way that we do today. It took about 100 million years, we think, for the first stars to form. These were massive balls of hydrogen, pure hydrogen almost, known as population 3 stars. So you think of hydrogen and helium, it's even older than the stars that we can see in the sky. I had to update this slide thanks to the James Webb Space Telescope. At the moment, we think the oldest galaxy that we've seen formed about 300 million years since the Big Bang. And star formation, the rate that stars are formed in our universe, peaked 4 billion years into the universe. So that's about 9 billion years ago. Now, the stars themselves, of course, have a profound effect on the chemical composition of the world. In stars like the Sun, hydrogen is being fused into helium. So you take two hydrogen atoms, you smash them together, you create helium, and you release the energy that powers the stars. And so even when the first stars were born, they began to change the composition of our universe. The Sun itself, which is the subject of this picture with a graphic overlaid, has been fusing hydrogen to helium for about 5 billion years, and it's going to do it for another 5 billion years more. Once stars have run through all of their hydrogen, they enter what's known their red giant phase. So the star runs out of hydrogen, the outer layers collapse down inwards, and that collapse raises the pressure, raises the temperature, and provides the conditions that you need to start smashing helium atoms together and building heavier and heavier elements. So a star like the Sun, when it runs out of hydrogen, will begin to fuse helium. It will swell up to about the size of the Earth-Sun separation, so it becomes really a giant star, a red giant star. And it will begin the process of fusing helium into carbon. Now that's more or less all the Sun's going to be able to do, but for even more massive stars, you're then able to take carbon. You have the same process, your helium will run out, your star will collapse, it will become hot and dense in the core, and the conditions are right to begin fusing carbon into oxygen, and so on and so on. You can fuse hydrogen to helium, helium to carbon, carbon to oxygen, to neon, to magnesium, to silicon, and then you get to iron. Now iron holds a particular place in the periodic table, and you can see there that it's being referred to as iron ash. This is probably the most technical slide that I'm going to show, so I'll walk through it. Iron is the most stable element that we know of, and so it will never give you more energy than you put in. What I'm showing here is what's known as the binding energy per nucleon. Basically, if you move upwards on the graph, you'll get energy out. And from the left-hand side moving right, you can see the process of nuclear fusion. You might be familiar with the concept of we're trying to unlock this as a power source. So fusing hydrogen into helium, you can see from the steepness of the graph in that region, releases a lot of energy, and all the way up to iron in the middle. On the other side, very massive elements like uranium on the far right release energy through nuclear fission. So if you break a uranium atom apart, you'll get out energy. And that's what we do currently in our power plants. And you can do that all the way down, breaking down atomic nuclei until, again, you reach iron. If you add protons or neutrons to iron, it will take energy. If you try to break it apart, it will take energy. So as you can probably see, it's going to make a terrible fuel for our star. And once the star's got a significant iron core, the collapse is uncontrolled. It collapses all the way down to nuclear densities. The outer envelopes bounce off the center of the core, and it explodes, like in the animation here. And this is a supernova. So stars have spent their life assembling atoms all the way up, elements all the way up to iron in the periodic table. But even in these spectacular explosions of the most massive stars, they go on changing the composition of elements. This slide's sort of an advert for our observatory, which is about 6 miles from here on the south edge of Birmingham. It's called the Wast Hills Observatory. And back in May, some PhD students went out and took an observation of the object that's being pointed to by the blue arrow. That's a supernova in the Pinwheel Galaxy, which is about 18 million light years from Earth. So this thing exploded since the dinosaurs, and in astronomical terms, it's very nearby. And that's what we see when a supernova happens. A new star apparently appears. Now, because they don't need to be stable anymore, you don't need to have this balance of the star being held up, you can actually, in supernovae, begin to form elements even heavier than iron, because you can take the energy of the supernova and forge it. And so supernovae, for example, begin to form things like nickel and cobalt, which are the main power source for them. And they leave us with these beautiful supernova remnants, which is the subject of the slide here. This is Cassiopeia A. It's located in the Milky Way galaxy, about 11,000 light years from Earth. And it exploded about 350 years ago. It's now 10 light years across, and when we point our X-ray telescopes at it, in this case, you can see the different colours are showing us the different elements that we can see within this sort of leftover material from the massive catastrophic death of a star. So silicon, helium, iron, and actually even heavier elements. So even in their final death throes, as supernovae, just like the ones I showed on the very first slide, stars are changing the chemical composition of the universe. And when we look around us in the solar system, we see, of course, the signatures of these processes. We see hydrogen and helium, which are as ancient as the universe itself, lithium as well in trace amounts. We see the products of nuclear fusion in stellar cores, so oxygen, silicon, all the way up to iron, and we see the products of supernovae, elements that are slightly bigger than iron. But as we've all seen, and I've mentioned some of them already, there are far bigger elements than that, and supernovae are not capable of making them. And so we need a process even more powerful than the deaths of massive stars that collapse in on themselves and forge huge nuclei in their cores. And that process occurs, to the best of our knowledge, in neutron star mergers, like the one I'm showing here. Now these have some remarkable observational properties that I'm going to go through one by one, but you can see even in the image there's these sort of wobbles on the edge of the page, which is this very sci-fi term, ripples in space-time, gravitational waves, which we're now able to detect. You can see from the poles of these two massive things colliding together, blasts of energy shooting out into the universe. And these really are the crucibles for some of the most massive elements that we see around us. So let's slow it down a little bit and ask, what is a neutron star? This is the model of an atom. This one in particular is a helium atom. It has 2 protons. That's what makes it a helium atom. And that is a tight nucleus of protons positively charged, neutrons that are neutral, and electrons that go round them in these orbitals at some distance away. Now, electrons don't like to be near one another. So in a solid like our bodies or this room or anything like that, the electrons are repelling one another and keeping the shape of the solid. Electrostatic repulsion, it's called. So you can squash them and they'll resist, just like trying to crush a brick with your hands. It's not going to go anywhere. If you can apply enough pressure, the electrons will steadfastly refuse to touch one another, and that really only gives them one option, which is to retreat towards the nucleus of the atom. Now, if you do this to the extreme, so that all the electrons are as compressed together as is possible to do, you'll end up with a body that looks a lot like this. This is a white dwarf, and it's the endpoint for our sun, and any star really up to about 8 times the mass of our sun. All of the atoms have been crushed down to the point that the electrons are almost touching and are very close to the nucleus of their atoms. These things are very dense. This has about the mass of the sun, so an entire sun's worth of material has been squashed down into the space of the Earth. But what happens if you keep applying pressure, and you can probably tell a hydrographic designer for this, you eventually will force those negatively charged electrons into the positively charged protons, and you'll end up with neutrons that are packed as tightly together as it is possible to be before being crushed down to a singularity. And that configuration gives you a neutron star. So neutron stars are unimaginably dense. They're bodies that are about 1.4 times the mass of the sun, maybe up to more than 2 times the mass of the sun, that have been crushed down under their own gravity to an area roughly the size of Birmingham. Now you can imagine the incredible amount of energy that's been stored away in a body like that. And to give some context, and I put it on the slides, if you had a teaspoon of material from a neutron star in Earth's gravity, it would weigh over 100 million tons. So balanced on your teaspoon, which you couldn't possibly lift, is roughly the weight of 10,000 Eiffel Towers. Really unimaginable amounts of pressure and density. And this is the final state of material before, if you add too much pressure, you're going to end up with a black hole. So neutron stars are reasonably common in the universe. We see them in our own galaxy, doing all kinds of interesting things like ripping stars apart, etc. And they're one of the endpoints of stellar evolution. So stars are born in massive clouds of gas, known as nebulae, which eventually condense down under their own gravity and initiate the conditions for nuclear fusion, where they enter what's called the main sequence. That's where they burn hydrogen for, depending on the size of the star, millions or even billions of years, enter the red giant phase, and for a star like the Sun, eventually blow off their outer layers in a planetary nebula like at the top of the graph there, and end up as a white dwarf about the size of the Earth. All that time creating heavy chemical elements and enriching the universe. For more massive stars, you'll get the supernova like I showed, and if they're between about 8 and 20 times the mass of the Sun, eventually they'll be crushed down into a neutron star. Anything bigger than about 20 times the mass of the Sun collapses all the way down to being a black hole. And it turns out from observations, most of the stars in the universe are orbiting with a partner. They're in a binary configuration. So there are fewer single stars than there are partners in a binary. So once all of this evolution is done over millions or billions of years, you're left with 2 neutron stars, assuming they've survived all the various explosive processes that can rip the binary apart, 2 neutron stars drifting together in the emptiness of space. And over the following billions, tens of billions of years, they slowly spiral towards one another, with their orbit decaying due to gravitational waves, which are these blue arcs rippling away into space. And that takes an extremely long time to do, and not a lot happens because these gravitational waves are very faint, or very quiet is the term we use, and hard to detect. But in the final few seconds of their dance together, something quite incredible happens. I'm going to show a simulation here, but I'm going to quickly talk through it so that it makes some sense. This is the final moments, really few seconds, of 2 neutron stars merging together. It's one simulation, but visually it's split into 2 halves. On the left, the yellows and reds are showing you the material, the density of that material, where yellow is the most dense, red is the least dense. And on the right, you're seeing the magnetic fields. Now, all magnetic fields in the system are extremely strong, but green is the most strong. So let's have a look at what happens as these 2 approach one another. They begin orbiting around, they're just changing colour as they go into the different sides of the simulation. You can see magnetic fields in the disk, and as they begin to spiral together, they start to tear each other apart, and the magnetic field is stirred up into this incredible disordered structure, and you're left with a whirling maelstrom of material in the middle of the screen. You may see a white shape beginning to appear in the centre. That's actually a black hole. And that black hole now is being threaded by an intense magnetic field which has ordered itself into this funnel shape through the core of the black hole. And so you can see that the material is swirling around the compact object at the centre, and we now have an ordered magnetic field threading it from top to bottom. This is effectively the crucible of all the heaviest elements that we see on Earth. So any of you who happen to be wearing gold on your finger like I am, or earrings, or have, I was going to say used uranium, but I hope none of you have, in a power plant, this is likely where it all comes from. So I'll talk through some of the things that happen, but the main place where our heavy elements are coming from is this swirling disk surrounding a black hole in the centre of the screen. So what's going on there is a process known as R-process nucleosynthesis, which sounds very fancy, but the R just stands for rapid, so it's fast nucleosynthesis. You're building atoms quickly in this environment. And the reason that can be done is that any atoms that are sitting there in that disk are being bombarded with neutrons so fast that they can't have them decay away before so many have stuck to them that there's suddenly this massive unstable isotope of probably iron, which is what's left over in the crust of the neutron star. Once that's happened, and eventually a beta decay will happen, so an electron is ejected and a proton is created in the core, and I've been saying a few times that the number of protons tells you what element you have, you've built a bigger element. And that happens many, many times within about a second of the neutron star merging. The radioactivity of these extremely massive and unstable isotopes heats the surrounding environment and causes it to glow. And we can detect this glow. It's called a kilonova, and it's one of the hottest topics in astronomy at the moment, is the detection of the radioactive glow of very heavy elements being created in processes like the one we saw on the last page. This is from a paper by Stewart et al. That came out just last year, and the goal of this paper was to come up with a realistic rendering using real nuclear physics and radiation transport codes to show what this might look like at a distance of roughly several hundred Earth-Sun separations away. So the scale of this, you can probably see on the left, this is what a kilonova looks like about a day after the mergers happened. The scale of 100 AU means about 100 times the distance to the Sun, so that'll give you some idea of the size of these. And on the right, this is about 20 days after the merger, and it's expanded to about 1,000 times the Earth-Sun separation. And you can see all the blues and reds, and those colours actually have meaning. In the red regions, like this band around the centre of the merger, some of the most massive elements are being formed. And it's red because the material being formed is so big and so complex, it has so many electron orbitals, it actually blocks visible light from getting out. And so it's coloured red, but what it actually is infrared. It's got a bright infrared glow. In other regions where we have the blues, less massive material is being created, and so some of the optical light is escaping. And so when we observe kilonovae, we can see from the colour some idea of the mass of the elements that are being created. So whether they're smaller things like something like strontium, or very massive things like, for example, gold, and bigger. Now, I mentioned we've detected these. We found our first one in 2013. Now, you'll have to forgive the somewhat grainy image. This is by the Hubble Space Telescope, but it is looking about 6 billion light years away when it's attempting to do this. The object in the left panel from June the 13th, 2013, you might just about make out a sort of fuzzy red blob within that galaxy. And a few weeks later, on July the 3rd, it had vanished. And that's the speed of evolution of kilonovae. They're extremely difficult to track because their radioactivity, the half-life of these elements, decays fairly quickly, and so the transient is not that bright to begin with and fades fast. But when we model the evolution of this transient, we learned that heavy elements that total about 3 to 30% the mass of the Sun were created in just one event. So these are prodigious creators of heavy elements. So I mentioned, well, I got on the slide that this was found following something called GRB 130603b. And neutron star mergers have another trick, kilonovae being very difficult to detect, fortunately have other tricks that allow us to find them and follow up and make discoveries like this one here. Those are called gamma ray bursts, and this is an artist's impression of one. Think back to the simulation several slides ago when I showed an ordered magnetic field had formed along the poles of this merger. That actually allows material to be accelerated to basically the speed of light, 0.99999, however many nines you want, times the speed of light. And these are relativistic jets that are blasted out into the universe from the poles, which is being depicted by these blue things exiting here. Contrary to kilonovae, which I mentioned are very faint, gamma ray bursts are actually the brightest thing in the universe other than the Big Bang. The image I've got here is what the sky looks like in gamma rays, the whole sky. The bright yellow band across the centre is our own galaxy, the Milky Way, and there are various radiative processes going on there that are emitting gamma rays that we can detect. And you can see dotted around the sea of blue are reds and yellows that are gamma ray sources coming from distant galaxies. And this little flicker, which is an animation, I'm afraid, not a real gamma ray burst, is a GRB. We detect these probably once a day, coming from some distant part of the universe. We can see them from even sort of 1 billion years or less after the Big Bang. They're that bright. And they only last seconds, some of them last minutes. There are actually different types. But in the time that they shine, they outshine the entire universe momentarily. That's the incredible energy release of two neutron stars coming together and firing off these jets. Now, there's one other trick that these things have that allow us to detect them, and I already showed some, the beautiful blue arcs of the two neutron stars spiraling together, and that is gravitational waves. And you may know, if you follow the news since 2015, that we can detect these using the LIGO interferometer, which is being shown in the lower left, in some very clever engineering techniques where lasers are fired down these perpendicular arms, and we measure the arrival time of those lasers getting back. And if they differ by tiny fractions of a second, we know that the universe effectively wobbled in that time, and some gravitational waves passed through Earth. There is a particular event that is probably the most impactful scientific discovery of the last 50 years, somewhat arbitrary that, maybe not as much as 50, but certainly recent astronomy, which is the advent of what's known as gravitational wave and electromagnetic, i.e. light, multi-messenger astronomy. So there is one source in all of human history that we have detected both gravitational waves and electromagnetic radiation on. And it happened to be a GRB, 1708-17A, and a gravitational wave source, 1708-17. So let's listen to the sound, hopefully this is going to work, of both of those things. And I want to say before I start the video, I really don't like the sound NASA picked for the gamma ray burst, because I've spent a lot of time digging them up as these huge explosions, and you'll see it's a little unsatisfactory. But let's take a look. Massive space explosion. What you heard and saw there is the ripples of space-time caused by two neutron stars that have slowly, well actually quite quickly spiraled into each other. You can see the time scale at the bottom there. This whole thing lasted 10 seconds, it was more or less in real time. And what you hear is an increase in frequency, which is the two neutron stars getting closer and closer and spiraling faster and faster and faster until eventually you hear that whip, which is known as a gravitational wave chirp, which is the moment of merger. About 1.5 to 2 seconds later, you heard a ding from a bell, frustratingly, which is the gamma ray burst that was seen associated with this event. And this remains, like I say, this sort of landmark achievement of modern astronomy, that we've got a gamma ray burst associated with the gravitational wave event, and it is the event that tells us what we long suspected is that at least some gamma ray bursts are coming from these two neutron star collisions. Here's what it looked like when we followed it up with optical and infrared telescopes. And this is actually the kilonova, which I talked about. This is the radioactive glow of heavy elements being created. So in the top right, the pre-discovery image, you can see the galaxy NGC 4993, which is catchily named. And about a day after that gravitational wave signal was detected, that gamma ray burst was detected, we tracked down this new blue transient sitting there in the galaxy, which clearly wasn't there before, just like our supernova that we saw from the West Hills Observatory. About a week after the merger, it had turned from blue to red, and that's telling us that the light that was trapped from very heavy elements near the core of the merger has finally made its way out and radiated in the infrared. And that tells us something about the heavy elements and the abundance pattern that's being created. So some statistics on this is that this was about 140 million light years from Earth, very close in gamma ray burst terms. They can be seen from the other side of the universe. And the gamma ray burst outshone our galaxy by a factor of about 445 at the time it exploded. So observationally, we can see these things going on, and we're starting to understand a lot about the birth sites of very massive elements. I should say there's still a lot to learn. So I showed a gamma ray burst before with this little flicker of a few seconds of emission. We don't think that gamma ray bursts from two merging neutron stars should last more than about 2 seconds. And the reason for that is that's the time it takes the black hole made by the merger to eat up all the material from that whirling disk I showed in the simulation. In 2021, I haven't mentioned yet, gamma ray bursts are named for the inverse of the date. So this one is from the 11th of December 2021. And naming them for the inverse of the date helps the European and American astronomers agree on what to call them, so it's a very useful trick. This one lasted about a minute, and actually this is a sign that there is some new physics going on that we don't understand in these things. It's possible that the neutron stars merged and remained as a neutron star. That would teach us something fundamental about how easy it is to crush neutrons down into a black hole. It's possible we saw a neutron star that was actually shredded apart by a black hole in this case. And it's also possible, and probably most likely, that we just don't know the physics of these things as well as we like. And so in the last 2 years, there's been a real revolution in our understanding of these kinds of explosive events. We know it's a merger because we found its kilonova. this fast-evolving radioactive transient just hanging there, the red orb in the nothingness of space. And you can see it's by far the reddest thing in the image. It's very strong in the infrared and faint in the optical. So this image is a Hubble Space Telescope image of the field. The host galaxy is the lovely elliptical one in the centre there, and the kilonova counterpart is being pointed out by the blue arrow. This one is a little further away, 1.2 billion light years from Earth, but much, much more powerful. It outshone the Milky Way by about a factor of 3.8 million. It's one of my favourite gamma ray bursts, but I won't get into the reasons for why. Next, we found this one, which is even more powerful. This is actually the second brightest gamma ray burst ever detected. So I've told you that these are the most powerful explosions in the universe. This is the second brightest one we ever saw. And it turns out that it too was from a merger. So this problem of not wanting them is the wrong word, but not thinking they should last more than 2 seconds is in real jeopardy because these incredibly powerful things keep producing these red orbs, synthesizing gold and thorium and tellurium out there in the universe. This one outshone the entire Milky Way by a factor of 9.6 million. So I just keep hammering these statistics home to really reinforce that these are the most powerful explosions that we know of. And this one is particularly interesting because you can see that the host galaxy, which we've labelled in the lower right there, is quite a long way away. In fact, it's about the length of our Milky Way galaxy away. But based on all of the arguments you can make, probabilistic arguments of the likely host, observational arguments based on modelling, and even actually spectral identification arguments that we've seen, that is the host galaxy. And that tells us that these two neutron stars spent billions of years orbiting together, having been kicked out of their home galaxy at probably hundreds of kilometres a second, likely due to the supernovae they experienced whilst they were evolving to become neutron stars. If you saw the news, this one came out about 2 weeks ago from a collaboration that I was working with, and it's been a really exciting event to work on. You can see how red it is from the images at the bottom, which are basically colour filters. The bluest one on the left and the reddest one on the right, you can see it's barely detected in the blue filters, which actually visually would be red. And then way into the infrared, you can see how bright it gets. And one of the reasons that we can learn so much about these days is the launch of the James Webb Space Telescope, which has been flying for about 2 years now, wasn't available for GLB 211211A, but is proving to be an incredible tool for understanding the origins of chemical enrichment in our universe. The reasons for that are that it's got this incredibly huge hexagonal mirror that's enormous, collects a lot of light, lets us stare a long way into the universe, but also it's powerful in the infrared. And as I've been mentioning, that's exactly where these sources seem to be radiating. So we were able to take a spectrum and identify actually the signatures of specific elements being created in this merger, the one I showed 2 slides ago. So you can see basically this bump here that's in the green model, the orange data and the black data. We've now seen the element tellurium in 2 different kilonovae. And that tells us that the conditions are right for very massive elements being created. Tellurium has an atomic number of, I think, 52, an atomic mass of about 127. So this is really one of the bigger elements out there, and we now have what looks to be fairly concrete evidence of it being created. I actually brought some with me, let's see. So hopefully that shows up. So it's this shimmery metallic-like material. Of course, when it was first formed and radiated like we've seen, it was a gas, but it's crystallized and it's now here on Earth. This is probably the ash of a neutron star merger that happened likely several billion years ago, somewhere in this galaxy, and has been mixed around our galaxy to end up on Earth, where it's used, I think, primarily for coating electronics. It's a fairly rare element anyway. But there it is, the ash of a neutron star merger. And with observations like the one I just showed, and actually the suite of observations that I've just showed, we're starting to fill in the periodic table of very massive elements. So this graph is coloured by the processes that made them. And think back right to when I started talking, the hydrogen and the helium that's as ancient as the universe. The lower mass elements, really starting from carbon, nitrogen, oxygen, etc., that were built up in the cores of stars. This graph is actually coloured for explosive events, so you can get them from exploding stars as well, of course. All the way up to iron, which refuses to be fuel for anything, and so you need a new process, like a supernova, to create more massive elements. And then you see where the purples take over, where the only process that we really know of that creates elements of that mass is likely to be the neutron star mergers. And you can see now that we're starting to fill these in. The first, the gravitational wave event, 1708-17, was the first identification of an element. That was strontium, over on the left there in green. I've highlighted tellurium in red as well. These are the ones we're confident of. But all of these very heavy things, including things like gold, which I included in the title of my talk, and silver, and even lanthanum and actinium, are being created in mergers, just like the ones I've been showing. And so I'm going to show a video now, which really puts all of the pieces I've been talking to together in terms of neutron star mergers. And I'm going to be quiet and let it run, but let me talk through it before I do. What you're going to see are the final seconds of neutron stars coming together, spiraling closer and closer, releasing blue arcs of gravitational waves, which we now, since 2015, can detect on Earth. They'll come together and they'll launch these beautiful jets of the gamma ray burst, relativistic jets streaming out all the way across the universe, which we've known about for approximately 50 years. And then you're going to see a big cloud of material that's first blue and then turns red as the light being blocked by heavier and heavier elements comes out, the kilonova, which we've only known about for the last 10 years, since 2013. And as you watch it, I'd like you to think about if you're wearing any gold on your finger, or if you gold in your earrings, or the uranium in nuclear reactors, the thorium in the core of the Earth, iodine used in medical processes. All of those heavy elements likely came from an explosive event that looked a lot like this. Thank you for listening.
Thank you so much. That was really interesting, and really appreciate you bringing in the tellurium.
I forgot to say I was given that as a gift, actually. For the project I showed, GLB 230307A, we were given some tellurium because that was the key result. So it's quite a nice thing I keep on my office shelf.
It's amazing. It's
nice to be able to bring it along.
Yeah. And so we, as normal, at these lectures, we have just got a few minutes if anybody's got any questions they'd like to ask. So have a think and hands up if you would like to ask a question.